Hello everyone, welcome to my video presentation. This is my paper TokenPowerBench, which is accepted by AAAI conference in 2026. The title is TokenPowerBench benchmarking the power consumption of large language model inference. The author is me and Dr. Wei Zhang from Texas Advanced Computing Center and Jie Li, Yongjian Zhao, and Tongyan Wang from Texas Tech University, and Dr. Xi Wang from Southeast University, and my advisor, Dr. Chen from Texas Tech University. Yeah, so this is an overview of the TokenPowerBench. For now, the model services need to consume a lot of power, and from some literature study, we know the inference has dominated the power consumption instead of the training. It accounts for like 90% of the total power consumption. But for now, there's no like comprehensive benchmark to measure the power consumption and energy efficiency of a large language model inference. So that's why we need to propose this method and propose these tools for academia and the industry world. So to the best of knowledge, our benchmark is the first lightweight and extendable benchmark designed for large language model inference. The benchmark combines like a configuration interface to combine like the benchmark configuration, prompt DSS, and the benchmark engines, and it has like a measurement layers that capture the CPU, DRAM, GPU, and total and the power consumption of the total nodes. Yeah, and after that we can generate a report to show like how much energy consumption during the process of the large language model inference. Yeah, so we can from this poster we can see like the second part is TokenPowerBench architecture. This is a benchmark which had a 3-layer architecture. The first one we call it like configuration layer, and second one is execution and measurement. Then we have a report generation layer. In the configuration, we have like as you see, we can set different offline large language models. We can have different inference engines, and then we can have some prompt benchmarks. For the execution and measurement, we because we need to measure the power consumption, and the main component of the hardware is CPU, GPU, DRAM, right? So we use IPMI to capture the total power consumption of the node. We use Intel RAPL API to capture the CPU and the DRAM power consumption, and we use NVIDIA SMI or some NVML library to capture the power consumption of GPU component. And during the life scale, like life cycle of the large language model inference, we divide them into prefill and decoding phase. And for the prefill, it means the time to the first token. We can also measure them based on the like the IPMI, NVIDIA SMI, and the IPL. And for the decoding phase, we can also use the similar ways, but it's different, right? We have a spatial view, like where the power consumption is spent, like in CPU or in GPU or in DRAM. And we can also have a temporal view, like when the power is spent, during the prefill or during the decoding phase, right? So after that, we can capture, we have a database to store all of the power consumption information. And after that, we can calculate the several matrix. For instance, we can capture the total energy consumption, like energy per token, energy per response or energy per second. That's the three of the key matrix we want to evaluate. And after that, we have done the experiments on our facilities. We are using GPU, NVIDIA H100 GPUs. We have 32 H100 GPUs to deploy the offline language models. So we start from the single node to cross node. For the single node, like the Llama 3, 1 billion, 2 billion, or 8 billions. Yeah. So as you see here in the third part in the experimental results, so we capture the energy consumption during the prefill and decoding phase, and after that we can see the like the popular open source language models, like the Llama 3, like the Mistral, like the Craven, like the and Falcon, Falcon. So and they are all in a single node, like either one GPU or at most 4 GPUs. In this case, we use different engines to deploy these language models. We use the VLM, Tensor RTLM, and transformers and deep speed. So we found the VM is the most efficient energy to deploy these language models. Yeah, and you can see it from the figure. And at the same time, we want to like evaluate how the parameters affect the energy efficiency. Like you see from the same settings or configurations, you can set different workloads, like the how many batch sizes you want to set, and what is like the different parameters, like 1 billion, 3 billions, and 405 billions. They must be very different, right? So we have already used our method experiments to evaluate this one. So for instance, in the figure 3, we use the heat map to measure like the how the SOTA language model consume the power consumption. So as you see here, the SOTA is like the Llama 3, 405 billion is one of the largest open source language models. So we need to use 10 H100 GPUs to deploy this one. So we use 3 nodes or 4 nodes, but we set different batch sizes to process different workloads. And as you see here, in the heat map, so the darker color means the energy efficiency is worse because it consumes more energy to generate one token. So so this is some takeaway message you can have. Yeah, and for the third picture in the experimental results, as you can see here, we want to evaluate the batch sizes. We evaluated the batch sizes from 32 to 1024. So it means you need to you can how many prompts you can process at the same time. As we expected, so if we enlarge the batch sizes, the energy consumption would be worse. So energy efficiency would be worse, right? So, but it can process more result, more prompt, and generate more outputs. It's kind of like trade-off between the performance and the energy efficiency, right? So, and actually, in my paper, we also evaluate like the quantization or contact length parameters. But we cannot show them in the poster. So if you are interested in the detailed experimental results, please feel free to download my paper and read it. And the conclusion is like our benchmark is the first lightweight, extendable, and reproducible framework to benchmark the power consumption and energy efficiency of language model inference. And we have shown some important results of the popular and open source language models. So please feel free to reproduce them or to use my code. And we will also extend our results to some other kind of NVIDIA GPUs or AMD GPUs, right? So like the Ampere 100 or Blackwell or AMD MI series. Yeah. So and in the fifth section, so we have the three QR code. The first one is a Repax website. Is what we are running. So it is a new HPC facilities. So it's like a it's where I perform my experiment. Yeah. So if you are interested, it's also one of the NSF access projects. So if you want to use the GPUs of Repax, please feel free to apply in the NSF access official website. And the second one is GitHub Rebel. So if you are interested, please feel free to download and use the code to run it on your own HPC data center. And the third one is the video presentation. So if you can scan it to learn like the oral presentation of my paper. Yeah. Thank you so much for your listening. Thank you so much for your time. Yeah. And if you have any other questions, feel free to email me or leave me a message. Yeah. Thank you so much.